Here we have a solubility problem where they're asking us if a precipitate would form given that two solutions of salts are mixed together. And they give us a nice hint. They say the potential precipitate here, whose KSP value is given, is magnesium hydroxide. Well, the two salts that are being mixed together contain the ions that make up the potential precipitate. We have magnesium and hydroxide. Let's start with writing an equation for the dissolution of magnesium hydroxide. And let's consider values for K and Q and see how those compare. As I'll bet you can do in your sleep at this point, writing an equilibrium expression is not much of a challenge for you. We would take just the aqueous species, not the solid, and multiply them and raise them to the power of their coefficients. Note that the hydroxide has to be squared. They give us an actual numerical value for this in this problem. They say 8.9 times 10 to the negative 12. In order to figure out whether or not a precipitate forms, we need to make a comparison of Q to K. Well, if they're equal, then the system is at equilibrium. If Q is less than K, then we would shift right in order to reach equilibrium. And if you look closely at this equation, the species on the right side of the equation are aqueous species. So a shift right would mean no precipitate forms. The other possibility is Q being greater than K. In that event, in order to reach equilibrium, think back to chapter 13, we would shift left. Well, the species on the left side of the equation is a solid. Shifting left, or forming more of the solid, means that we would precipitate. So if Q is greater than K, then a precipitate forms. If Q is less than K, no precipitate. And if they're equal, well, then the system is already at equilibrium. Now, in order to figure out whether or not a precipitate forms, we need to do some math. So let's take a look at the two salt solutions that are being mixed together. 100 milliliters of in my case, the red number is 5.4 times 10 to the negative fourth molar magnesium nitrate. If I multiply the volume times the molarity, I'd get the number of moles of magnesium present in that salt solution. I get 5.4 times 10 to the negative fifth moles because I multiplied the volume by 0.1 liters, or 100 milliliters. We'll do a similar calculation for the hydroxide ion in the other salt. 0.1 liters times, in my case, the red number is 6.0 times 10 to the negative fourth. So that gives me a number of moles of hydroxide that's 6.0 times 10 to the negative fifth. So now we know the number of moles of each of the ions that make up our potential precipitate. In order to find their initial concentrations, we would have to divide by the total volume. You can always presume, unless told otherwise, that the volumes of two solutions being mixed together can be added to get the total volume. In other words, volumes are additive. They can be added together to get the total. So, to find the initial concentration of magnesium, and I denote that with the little subscript 0 outside the brackets, we would take the number of moles that we had calculated here and divide by the total volume in milliliters. Or actually, we'll convert it to liters. 200 milliliters converted to liters is 0.2. And when we divide that out, we get 2.7 times 10 to the negative 4th molar. Now we have an actual concentration. We'll do the same calculation for hydroxide, taking the number of moles we calculated up above and dividing by the total volume. Notice that the total volume is the same for both ions. And in this case, it works out to be 3 times 10 to the negative 4th. Okay, so far so good. We've got an equation, we've got an expression and a numerical value for K. In order to find Q, we calculate it the same way as K, except we get to use conditions that don't necessarily represent equilibrium. Importantly, don't forget to square the hydroxide. That needs to show up in both equations for K and Q. And we'll just plug in the numbers that we had worked out. For magnesium, in my case it was 2.7 times 10 to the negative 4th. And for hydroxide, 3.0 times 10 to the negative 4th. Don't forget to square that. And then punch that into your calculator. In my case, I'm getting 2.43 times 10 to the negative 11th. Now we need to make a comparison of Q to K. Which one of those numbers is bigger? In my case, for my red numbers, and this may differ from student to student, but I've got a value of Q that is actually bigger than the value of K. So if Q is greater than K, then according to my calculations, we would shift left and form a precipitate. Now some students will get red numbers where the calculated value of Q is less than K, in which case there would be no precipitate. So you have to actually work the calculation to figure out which of the two boxes you can check, and then just state your value of Q in the blank.